Hello guys, and welcome to a video on tangents and normals, stationary points, second order derivatives, increasing, decreasing functions, and that's it, I think. Yeah. So let me just explain briefly what a tangent and a normal is to a curve. So if you have the curve y equals f of x, this looks like this looks like a cubic equation. So this is at a little point A. So the tangent of the equation is this specific bit here. So it's essentially it's basically just an increase, and it's a tangent which is curving essentially away from the curve. Whereas the normal is perpendicular to the tangent. So the normal is the reciprocal of the tangent, and it's 90 degrees from the tangent. So we're just going to go through two examples and you'll get it straight away. It's fairly easy, fairly normal, and you should be able to get it straight away. So I'll just put up these two examples right now. Okay, so we have an example here. So we find the equation of the tangent to the curve y equals x cubed minus 3x squared plus 2x minus 1 at the point 3, 5. We're just going to assume that's 3, 5 for a second. This is just y equals fx. So what are we going to do here? So from your knowledge from the last two lessons, we're going to differentiate y equals f of x. So dy by dx, the derivative of y with respect to x, is equal to bring down the power, times that by x, and subtract the power by 1. You do the same thing here. So minus 6x, that's it. 6x to the power of 1 if you prefer, plus 2, and then the 1 is a constant, so it gets dropped off. So now we have our gradient here. So what we're going to do, we are going to substitute 3 in. So we're going to put, so when x equals 3, so we have so dy by dx is equal to 3 squared minus 3 plus 2, which is equal to 27 minus 18, which is 9, plus 2, which is 11. So the gradient, which we're going to call mt, m usually stands for gradient, and we're going to put a little subscript called t, which stands for tangent. And the gradient's going to be 11. So we're going to use a formula. We're going to use a formula of an equation of a straight line. And I'm going to put this in red pen here. So this equation is defined as y minus y1 equals m, where m is the gradient, x minus x1. So y1 and x1 are your set of coordinates which you are given. Hence the point 3, 5, where x is 3 and y is 5. Your y and your x you just leave as y and x, and your m is the gradient that you've determined. So since we're working out the gradient of a tangent, mt is equal to 11. So what we're going to do, we're going to substitute all our values in. So this turns into y minus 5 equals 11 bracket x minus 3. So what we're going to do, we're just going to expand. So y minus 5 equals 11x minus 33. And what we're going to do to fully put this as an equation of a tangent, we're just going to rearrange to put the 5 over. So therefore, the equation of the tangent at the point 3, 5 of this equation is equal to 11x minus 28. And that is our equation. It should be fairly simple. It genuinely is fairly simple. It's not a problem at all. And doing the normal is fairly straightforward as well. It's not a problem. I'll give you just a few exercises here and there just to answer. Okay, so we're going to move on to a normal, so I'll write an example next. Okay, so here's an example. So Find the equation of a normal to the curve y equals 8 minus 3 root x. Apologies for the messiness here. At the point x equals 4. Okay, so we're not given a set of coordinates, but we're just given one point. But that's no problem. We can easily solve this. We can make a set of coordinates if we do this right. So what we're going to do, the first thing is we're going to differentiate this. We're not going to differentiate because it's in the form 3 root x. So we're going to change this format to 3x to the power of the half. So y equals 8 minus 3x to the half. Okay, if when we differentiate that, the 8 gets rid of, and it's going to turn into 3 over 2 x to the power of minus a half. Okay. And now what we're going to do, when we substitute, we're going to put a subscript n. So the gradient of the normal is equal to when we substitute, when x equals 4, when we substitute this in, 3 over 2, 4 to the power of minus a half. So gradient of the tangent is minus 4 over 3. Okay? So now what we're going to do the reciprocal. So the reciprocal is where 1 a half is equal to minus 2. And the reciprocal of minus 2 is a half. So essentially a rule of thumb is that minus 1 over m is equal to m. This stays true. So what we're going to do, we're going to use the reciprocal. So the gradient of the normal is equal to 3/4. That should be relatively simple. And now we need to find our y coordinate. This is very simple. All we have to do is substitute x equals 4 into that equation. So y equals 8. Let me just draw that a second. So y equals 8 minus 3 root 4, which then equals 2. That's simple. And now we have the point. I'm sorry if this is very messy here, but just trying to make a point. So we're going to use the equation for a straight line, which is y minus y1 equals mx minus x1. That is our equation of a straight line for a gradient that passes through x1 and y1 at that point there. So y1 is 2, x1 is 4. So we're going to substitute all our stuff here. So y minus 2 equals 3/4 x minus 4. Okay, and so what we're going to do here, we're not going to put it into a general equation like y equals 11, y equals mx plus c. We're going to put it in something different. I hope you do have assumed knowledge of how straight lines work. So what we're going to do, we're going to times, oh dear, forgot about this. It's minus 3/4 here, and then 4 over 3 here. Do apologise about that. So 4 over 3. Do apologise for making that mistake. So what we're going to do, we're going to times everything by 3. So 3y minus 6 equals 4x minus 4. That is now one of our equations, is now the equation once we times everything together by 3. So what we're going to do, we're going to expand. So 3y minus 6 equals 4x minus 16. And now we're just going to rearrange. So now we have 3y minus 4x plus 16. So it's going to be plus 10 equals 0. And now this is in the form of ax plus by plus c equals 0. That's in the form. Sometimes they may want you to put it in the form of ax plus by plus c equals 0. And sometimes they might want you to put it as y equals mx plus c. But it just depends, really. So now I'm just going to give you just 2 exercises, and then we're going to move quickly on to increasing and decreasing functions. Okay, so here are two questions for you to do. So let me just read them out for you. So for f of x equals 12 minus 4x plus 2x squared, find the equation of the tangent and the normal at the point where x equals minus 1 on the curve where y equals f of x. So find the tangent and the normal, and then you'll know what to do from there. Now question 2 is worth 6 marks. So the point P with x coordinate half lies on the curve y equals 2x squared. The normal to the curve at P intersects the points P and Q. So find the coordinates of Q. So what I would suggest to do is find your y, so find your P coordinates, and then also maybe use the discriminant to find the value of m when the line just touches the curve. That's my suggestion. But also, optionally, I would draw a sketch showing the curve and the point P to the normal. This will make sense and help you check that this will help you check that your answer makes sense. So good luck with these, and I will reveal these answers on the description of the next video. So good luck with these questions. Okay, so now we're going to be moving on to increasing and decreasing functions. This is fairly simple and it's not really much of a problem at all. So with increasing or decreasing functions, so if it's increasing the function of f of x on the interval of between a and b, so if you differentiate the function and you show that it's increasing for all values of x such that x is between a and b, so between the interval, and if it's decreasing, you have to show the equality sign is less than 0, and then you show what interval is f of x decreasing on. So I'll show you 2 examples, and I'll show you some exercises, and then we can move on to second order derivatives. Okay, so here's an example. So show that the function of f of x equals x cubed plus 24x plus 3. Show that the function of the function is increasing for all values of for all real values of x. So what we're going to do, we're literally just going to differentiate that. So differentiating the function of x is going to be 3x squared plus 24, and that's it. So now what we're going to do, so in fact x squared is a particular case. So x squared is actually for all the domain of x squared is all for all real values of x. So in fact 3x squared plus 24 is increasing for all real values of x because of x squared. So you have to put a statement that f of x is increasing. So f of x is increasing for all real values of x. And that's really simple. I'd be astonished if you didn't understand that. So we're going to move on to a second example, which is a little bit more typical. So I'll show you the next example now. Okay, so here's another example. Find the interval on which f of x is equal to x cubed plus 3x squared plus 9x is decreasing. Okay, so this is relatively simple. So what we're going to do, we're just going to differentiate straight away. You don't always differentiate. You might have to do some algebraic manipulation to get it into this format first. So we're going to do x cubed plus 3x squared minus 9x. Oh, sorry. So, when we differentiate, we will get 3x squared plus 6x minus 9. Okay, so then what we're going to do, so If it's decreasing, then we have to put this function as less than 0. So less than or equal to 0. That's what we're going to do. So we're going to factorize 3 out. So we're going to get x squared plus 3, plus 2x plus, minus 3. Oh, didn't get confused here. Is less than or equal to 0. Then what we're going to do, we're going to factorize this. So we're going to get 3, x plus 3, x minus 1 is less than or equal to 0. Therefore, the interval, so when we get our result, we get minus 3, and because it's less than 0, so minus 3 is less than or equal to x, which is less than or equal to 1. So the interval is decreasing, so f of x is decreasing on the interval minus 3, 1. Relatively simple, isn't it? It really is not bad, like, at all. So what I'm going to do, I'm going to set you some questions, and then just set you literally just 2 questions, so you just fully understand this. 3, actually. 3 questions, and then we'll move on to second order derivatives. Okay, so we just have a little bit of practice questions, so I'll just read them out to you. Find the interval for when f of x equals x to the power of 4 minus ax cubed is increasing. Question B, find the interval for when f of x equals x plus 25 over x is decreasing. And then question C is a marked question. So show that the function of f of x equals 4 minus x bracket 2x squared plus 3 bracket is decreasing for all x is real. And this is worth 3 marks. So I suggest giving all of these a go, and then you'll be secure on this topic. Okay, so now second order derivatives are just really easy. There's no point like fussing over it. Oh, second order derivatives. So if we have an equation of 5x cubed, dy by dx, as you know, you bring down the power and then subtract the power by 1. So it's going to be equal to 15x squared. Now, how do we get a second order derivative? You probably guessed it. It's going to be, we call this notation d2y or d squared y. D squared y is always, we call it d2y, it just makes everything easier. So d2y over dx squared is equal to 30x. So you're differentiating dy by dx again. So you bring down the power, 2 times 15 is 30, and then subtract 2 by 1. So it just makes the power of 1. But we just obviously don't include that. And that's it. That really is it for second order derivatives. Obviously with f of x, you obviously get f prime of x or f dash of x, but then d2y by dx squared is also 2 dashes, and that's it. That's literally it. So you just call this either double dash or whatever. You can call it whatever you want. So essentially, dny by dx to the power of n is equal to f dash of n of a function of x. That's essentially how this works, and this is fairly simple. I don't need to give you any questions because what is the point of it? Right, so we're going to move on to the big boy, and that is stationary points. Okay, so stationary points. What do these actually mean? So a stationary point is one of a local maximum, a local minimum, and a point of inflection. So this point A, where the graph turns from when the gradient comes from positive to negative, it is called a maximum point. When B, at the point B, when the curve goes from negative to positive, it is called a minimum point. So it goes from negative to positive, and a maximum, remember, goes from positive to negative. And at the point O, there's a thing that kind of is trying to be a maximum, but then slowly curves off as pretty much like a minimum. This is called a point of inflection, where the graph stays where the point, it kind of curves, and then the gradient stays the same. So in this case, this is a negative point of inflection. So it looks like it's about to become a turning point, but it doesn't. It still maintains the same gradient. So this is a point of inflection. Okay, so that's literally all you need to know. So negative to negative, or positive to positive. That's how this works. The plural of maximum is maxima, and the plural of minimum is minima, because you might have more than one maximum point or more than one point of inflection or minimum point. That's just how it works. So I'm just going to show you, see how many examples there are. So I'm going to show you 2 examples, and then I'll give you some questions to do, and then we can move on to integration. Okay. That's completely fine. Right, let's move on to some examples. Okay, so here's an example. So find the coordinates of the stationary point on the curve with equation y equals x to the power of 4 minus 32x. Okay, and then part B is by considering turning point, determine the nature of the turning point. Okay, so what we're going to do here is we're going to differentiate. So we're going to go on part A. So differentiating that. So dy by dx is equal to 4x to the power of 3 minus 32. And now what we're going to do with stationary points is quite special. So let dy by dx equals 0. So 4x cubed is equal to 32. We're just rearranging that. So 4x, that becomes 0, and then that equals that. Okay, so x cubed is going to equal to 8, and therefore the cube root of 8 is just 2. And so what we're going to do, we're going to substitute this 2 back into the original equation. So y equals 2 to the power of 4 minus 32 times 2. And in my head, so 16. So 16 minus 64, so that's minus 48, sorry. Minus 48. So 2, and you put a statement saying minus 248 is a stationary point. Okay, so 2 and minus 48 are stationary points. So let me just repeat what we just did. To find the coordinate of a stationary point, you differentiate the original equation. Then you let dy by dx equal to 0. Then you rearrange for x. So that's your gradient. That's what you found as x. Then you substitute whatever you found for x back into the original y equation to find your y coordinate of the stationary point. And that is stationary points in a nutshell. So what we're going to do is we're going to go on to part B. So what we're going to do, we're going to use our second order derivative. So dy by dx, as we found out, is 4x cubed minus 32. So what we're going to do, we're going to differentiate again. So we're going to say d2y is equal to dx squared. And that is equal to 12x squared. And that's it. Okay? So what we're going to do, we'll go whatever value you have found for dy by dx equals 0, so x equals 2. That is the value that we had found. What we're going to do, we're going to substitute that into our second order derivative. So 2 squared, and 12 times 4, that is 48. Very obviously, this is a minimum point. So this is a minimum point. Why is this a minimum point? So let me explain. So if d2y by dx squared is greater than 0, it's a minimum. If d2y by dx squared is less than 0, it's a maximum. If d2y by dx squared is equal to 0, then it's a point of inflection. So this is determining the nature of a stationary point. And so that is literally it. That is it. I'll show you a point of inflection because the problem with a point of inflection is that it could be a minimum and it could be a maximum, or literally it's just a point of inflection. So you will need to look at points at either side to determine if it's a minimum or a maximum. So what I mean is, when you found your x value, and when you substitute it back into d2y by dx squared, you have to determine if it's going to be a negative gradient to a negative gradient. So you set x as x equal to 1.9 and then 2.1, and then if there's if it's the same gradient, so if it's both negative, it's a negative point of inflection. If it's a positive to a positive, it's a positive point of inflection. And that's literally it. That is one example that we've used. So essentially, the second order derivative tells us the rate of change of the gradient function. So when dy, it's just simple, really. So I'm going to go through another example, and then that's it, and I'm going to set you some questions. Okay, so in this example, let me just read out the question for you, just in case you struggle to see. Find the coordinates of the stationary points on the curve with equation y equals 2x cubed minus 15x squared plus 24x plus 6. And so determine the nature of the stationary points. This is relatively simple to do because it's following the same step over and over again. And then I'll give you some step guidance to show that you can do this yourself. So, part A, what we're going to do, we're going to differentiate. So, dy by dx is equal to 6x squared minus 30x plus 24. Okay, so we're going to let dy by dx equal 0. That's what we're going to do from here. The next step is obviously setting this to 0. So now this is a quadratic. So 6 on the outside, and then this becomes x squared minus 5x plus 4 equals 0. So then literally this becomes 6, x minus 4, x minus 1 equals 0. So therefore, x is equal to 4 and x is equal to 1. These are our stationary point for the x coordinates. So now we substitute both of these back into the original equation. And so y equals sorry, let's call this x1 and make it x2 for simplicity. So x1 is equal to 4 and then our other stationary point is equal to 1. So y1, where x1 equals 4, so when we substitute 4 back into the original y equation, we will get minus 10. I already worked it out. And then y2, when we substitute 1 into this equation here, we will get 17. Okay? And then our coordinates, so we're going to call this point P. So one stationary point is at 4 minus 10, and then the other stationary point is 117. And those are our two stationary points. Okay? Hopefully that shouldn't be too difficult to follow. So, okay, we've got some stationary points. So, what are they then? Are they a maximum? Or are they a minimum? So now we've got to determine the nature of these stationary points. And the nature means, is it a maximum, minimum, a point of inflection? So let's have a look, shall we? So part B, we're going to differentiate dy by dx again. So d2y by dx squared, or you can put f double dash x. That's optional as well, but we're not going to do that for this question. Doesn't require it. So it's equal to 12x minus 30. 24 is a constant, so that gets rid of. So now we substitute our x values into our second derivative. So when x equals 4, 12 4 minus 30 equals 18, which is greater than 0. So therefore this is a minimum point, because it is greater than 0. Remember, if it's greater than 0, it's a minimum point. If it's less than 0, it's a maximum point. If it's equal to 0, then it's a point of inflection. Okay, so when x equals 1, 12 1 minus 30 is equal to minus 18, which is less than 0. Therefore, this is a maximum point. Okay? And that should be simple to figure out. I'm not going to show you any more examples. I'm just going to show you how to do the step by step. Oh, and one more thing as well. If you have d2y equals dx squared is equal to 0, then it's a point of inflection. Point of inflection, that's the abbreviation I'm going to put for it. So the point of inflection, so if then, now you have to work out your third order different derivative. So d3y or dx or d cubed y by dx cubed, but I prefer to call it d3y by dx cubed, is not equal to 0, then it is a point of inflection. Okay, so just to summarize then, if f of x is, if f of x is greater than 0, it is increasing in the interval a, b. If f of x is less than or equal to 0, then it's decreasing in the interval a and b. Such that AXB. Such that AXB. Okay. Equation, oh yeah, that should have been after equation of a tangent. Equation of a tangent is equation of a tangent is y minus y1 equals mt bracket x minus x1, where x1 and y1 are in coordinates. Equation of a normal is y minus y1 equals minus 1 over the equation of a tangent x minus x1, or just simply y minus y1 equals mn, where n is the normal, x minus x1. Okay? Okay, so for a second order derivative, d2y by dx squared is equal to differentiating dy by dx, which is also to equaling to d dx of y, if that makes any sense whatsoever. Or f dash of x is equal to f dash of x. So y turns into dy by dx, which when you differentiate that gives d2y by dx squared. And for the stationary points, so steps for the stationary points. 1. Differentiate y or f of x. Okay? Step 2. Let dy by dx equal to 0. So when you differentiate, let the derivative of y with respect to x equal to 0. Step 3. Rearrange to find x. Just x. Okay. Then find, when you've solved x, put x into the original y equation to find stationary points. Okay. Step 5, if there is a step 5, this is usually part A of a question, step 1 to 4. 5, find d2y by dx squared, or f double dash x. 6, substitute your x stationary value to find the nature. Step 7, if f double dash x is less than 0, it's a maximum. If f double dash of x is greater than 0, it's a minimum. If f dash of x equals 0, it's a point of inflection. A point of inflection, kids, remember that. And so if f triple dash of x is not equal to 0, then it is a point of inflection. If positive, then it's a positive point of inflection. If it's negative, it's a negative point of inflection. That's relatively simple, okay? So next time I shall teach you integration, and then just simple, easy, general integration, finding an area under a curve, and then this is literally it. That is literally it for AS differentiation. There is one more thing I have to teach you, which is modeling, but honestly, it's not really that difficult at all. All it is just show this, and then it's applying the stationary points in a proper modeling sense. I'm not going to teach that, as you can probably teach yourself it. Okay, so that's it. So let me show you steps here. So increasing, decreasing functions, equations of tangents and normals, second order derivatives, and whole steps of stationary points. So yeah, that's literally it, and I hope you have a good day, and see you next time when we do integration. Bye bye.